So I'm back together with Victor Smetacek today, and we're going to talk about the most frequently asked questions around ocean iron fertilization. And recently I was told a new storyline around why we had such a high iron deficiency in the ocean. And the math goes something like humanity killed 3 million whales, and a whale is defecating 7 to 12 tons of iron in its lifetime. So you could do the math, 3 million whales are dead, so 30 million tons of iron must be missing in the ocean. Would that be a fair calculation to basically blame a part of the iron deficiency in the ocean, which I've heard it's around 1/3 of the ocean has iron deficiency, that a part of that is due to industrial whaling, and that if we are framing the mission of ocean fertilization differently, we could basically say it's more like ocean restoration. We want to restore the iron levels back to the levels pre-industrial whaling. So we want to basically only put as much iron to the ocean as we robbed the ocean from killing all those whales.
Yeah, okay. What you have to remember here is that the whales, they might have had a lot of iron in them, but that iron, when they died, went down to the seafloor. That's not the real story. The real story are the intermediate trophic levels, the intermediate stages in food transfer from the phytoplankton to the whales, what's in between. And that is, of course, several times the mass of the whales themselves. The zooplankton, you need that much more zooplankton to feed the whales, right? And in that case, in the case of the blue whales, it was krill. So the biomass of the krill was huge. And that was iron on the fin, so to speak, on the move, right? And when that was eaten by the whales, then the whales released the iron back into the system, because when they ate the food organisms, the krill and the zooplankton, they were just getting blubber out of it. Look at us. We contain 4 grams of iron, each of us, right?
And you're iron deficient, I heard.
Yeah, I was for a time. But I had to take those same pills, iron sulfate, ferrous sulfate, that I was adding in the ocean, right? It's exactly the same compound, and which is a waste product of a lot of industries. So each of us contains 4 grams of iron, and to put it into a visual effect, it's 2 cubic centimeters, right? So a centimeter, 2, but this much metallic iron, right? Is what each of us carry. And that's also what the zooplankton carry. But the story about iron, which makes it so much more complicated, is that there's a lot of stored iron, storage iron, and partly to take it out of action, because iron is also detrimental. You can't have reactive iron roaming around in your cells, right? Because it reacts and creates these Ross species, Okay, I'm going into details. But I just want to let you know there are some things that are understood, but not by people in general, right? This stuff is just sort of being worked on at the moment. So this is what makes iron so complicated. So animals have a much higher demand for iron, but they also contain more iron because they also put more iron on the side, so to speak. I mean, zooplankton cannot divide like phytoplankton can. The algae behind you, right? Those are 2 cells that are dividing, these diatoms. Yeah. That's right. So if a parent cell captures some iron, it can immediately make daughter cells and share that iron. And the zooplankton cannot. And the zooplankton doesn't want to just leak the iron back into the system. It can store it. And the storage compounds are called ferritin. That's exactly what is measured when they take blood samples. They measure this protein, ferritin. And each protein can contain 4,000 and more atoms of iron, right? So it has a needle of metallic iron inside it. So that's what makes it complicated. When the iron gets into the zooplankton, then it can be activated when that zooplankton is eaten and digested and put back into the system. We have taken out not only the whales, because these were apex predators, but we've taken out all the intermediate stages as well. Also in the case of fish, I mean, all the fish swarms, all the anchovy, sardine and herring in the north. I mean, the coasts around Europe, they were thick with fish like a few hundred years ago. And that is the iron we are missing, because this was iron on the fin swimming around and picked up and retained and passed on. Right? So this seas of plenty of the hundreds of years ago, that's past. But we could restore it if we were to do it in an intelligent manner. With regard to iron, what binds iron is phosphate. Right? And these are both essential elements. And iron phosphate, ferric phosphate, iron 3 phosphate, is highly insoluble in the water when the conditions become, when there's less oxygen. Not exactly, it doesn't have to go into complete anoxia, I mean complete lack of oxygen, but when there's less oxygen, a lot less, I mean close to anoxia, then this ferric phosphate gets reduced to ferrous phosphate. And ferrous phosphate is highly soluble. So then you have an input of both phosphate and iron, and this is what the nitrogen-fixing blue-green algae need. So that's when they can grow, right? And that's what's happening in the Baltic. Because in the Baltic, you have a situation in the deep water where there's a lack of oxygen. And that's simply because that water has been down there for so long. It's a residence time problem. It hasn't had contact with the surface, because the surface, it can pick up oxygen from the atmosphere, but it can also help photosynthesis because of the light. So oxygen is only produced at the surface. It's either produced by the algae or it's taken up from the atmosphere. And that can only happen at the surface. So if you sequester water for a long time away from the surface, that water becomes anoxic over time. So you have that situation in the Baltic, and there you have these nitrogen-fixing cyanobacteria, because there's much more phosphate than nitrogen. And that's also because nitrate, NO3, contains a lot of oxygen, and there are organisms, all sorts of bacteria, that can breathe that nitrate, which is why ammonium nitrate is such a powerful explosive. So this nitrate has all the oxygen, right? So you get anoxia, you take out the nitrate, but you also add iron and phosphate, and that's when the cyanobacteria can move in and start growing, and that's fixing nitrogen. And there are a lot of people out there now who think that you can spur this nitrogen fixation and increase productivity. But again, that's not going to work, because for nitrogen fixation, you also need to have calm conditions. You need to have a situation where scum can form at the surface, because that's where the fixation is happening. And the Baltic is protected, and you can have scum in some bays, and that's why you have nitrogen fixation there. But if you go in the open ocean, there's very little nitrogen fixation going on. And with regard to the Gulf of Mexico, there you have the situation where the water from the Mississippi enters, is loaded with nutrients, but that water is also fresh. So it forms a kind of a cover on the seawater, and it makes this plume, Mississippi plume. And where it mixes with the seawater, with all those nutrients, you have a huge phytoplankton production, because you have a continuous supply of nitrogen and it's mixing. And so you're mixing the algae back into that and so on. It's transported out and still going on. But then below that, the water is stagnating, because you have this layer, this cover on the top. And that's where you have a huge oxygen deficient water mass in the Gulf of Mexico. That's the problem. That's how it's caused. Okay. Now, in the past, there used to be in this area a huge biomass of menhaden. Now, menhaden is a fish like herring. It looks like herring. I think it's a little bit bigger, but it's full of bones. And these are kind of deadly bones. I mean, these are really, heavy-duty bones. People are scared of eating this stuff, so they don't eat it. And they convert it into fish meal. I mean, they just dry the fish, powder it, and then feed it to pigs. And that is actually, I think it's the biggest fishery in the US. You never hear anything about it because people don't eat it. On the side, if you were to export that to Bangladesh, they love this kind of fish, because it's also in the Ganges mouth. It's not the same species, but it's a herring that is so full of bones. I actually had some of it, that you get scared, because the bones, they're not just bones, they also have barbs on them. So whoever swallows this menhaden type fish whole gets into problems. But the Bangladeshis or the Bengalis, they put the whole fish in the mouth, half the fish in the mouth, and then they pull all the bones out from the side, which Europeans wouldn't dream of.
I think I had the same fish in Bangladesh when I was visiting.
Okay. And it was full of bones, right?
Yeah.
It's delicious. Yeah, but then again, people are scared of bones. Anyway, so this menhaden fish stock probably has been fished a lot. And in the past, it's possible that this menhaden, just a swarm swimming around, would have been mixing the water more than now. Since they've been fished out or been fished down to much lower levels, there will also be less mixing. This is again something which is not considered. That when all these big animals were around, also the fish swarms, they were also mixing the water. And mixing, of course, always leads to more nutrients being available, because it brings it up from the depth. So that's another thing that we have to consider when we talk about restoring past ecosystems. That would be fantastic if we could start building up the original fish stocks along the coasts. Yeah, so that was the two examples, the Baltic and the Gulf of Mexico. And the Baltic, of course, is massively overfished. So there also used to be stocks of herring there and cod in the southern Baltic, but they've been declining, but not for lack of food. It's more because of overfishing, which is why they try to regulate them. But then there's so many countries involved along the Baltic, and they all want to have their share, and there are all these ships, there's fishing vessels, and it's a shame. But yeah, there's little hope.
And how could we fix the Baltic? So where does the excess phosphate come from? Is it all fertilizer from surrounding countries?
Yes and no. You see, if the deep Baltic gets anoxic, then the huge amounts of phosphate are mobilized from the sediments, right? Because the sediment is everywhere in the world. The sediments have a lot of phosphate. It's been sinking out and stuff, like dead fish. Their bones are made of phosphate, calcium phosphate. And that all stays down there. It doesn't come back up again. But if you have anoxia, and that stuff dissolves, and you then have mixing that brings it up again, then you have this input of ferrous phosphate. In the case of the Baltic, since it's overfishing, all you have to do is just stop fishing, for a while, if possible, which is not going to be possible. So I don't see much scope for manipulation in the Baltic, but this is what you could do. And of course, the Baltic, because of its low salinity, I did my PhD there when I was much younger. I know the place quite well. And because of its low salinity, the Baltic proper, further to the north, has a lot of freshwater cyanobacteria. These are nitrogen-fixing species, like Anabena and Aphenozomenon and so on, which don't occur in the ocean. Why are cyanobacteria restricted to low salinity? That's because that's the only place where they can do their nitrogen fixation, is my opinion. Like, there's not a single cyanobacteria in the Antarctic, in Antarctic waters, nothing. But the lakes on Antarctica, they're full of cyanobacteria. So it's not temperature. So there are lakes in Antarctica that have permanent ice cover almost, and there's these cyanobacteria growing there like crazy. This issue is not even considered in marine science circles. They don't even think about why are there no cyanobacteria, or why are there so few in the ocean and so on, right?
Toxic algae blooms in the Baltic Sea is coming from cyanobacteria blooms. And why are these cyanobacteria blooms not edible for the ocean food web? Why are they not yummy for zooplankton when in other parts of the ocean, algae present the base of the aquatic food chain?
Yeah, that's a good question. And not all are like that, of course. There are also cyanobacteria that are eaten. The Incas were growing that. So not all cyanobacteria are toxic, but that's true that a lot of them, I guess they're very ancient, and they have, to be able to do what they do, they need to protect themselves, because otherwise they would just be eaten. The scum would just be eaten. And scum is a very bad word. You feel repelled by scum, because in the past it has had its toxic effects. The cyanobacteria blooms in the Baltic, I don't think they've really led to deaths of any. It's not recorded that animals have died as a result. I know stories, individual stories, where some cows went down and drank some water and got the scum.
But the cyanobacteria blooms, they're always being blamed for the lack of oxygen. So if you talk to people about creating algae blooms in the ocean, they always say, oh, this is going to lead to low oxygen zones, because they think about, for example, the Baltic Sea or in the Gulf of Mexico. So for them, the chain reaction is, oh, the cyanobacteria are going to decompose and consume the oxygen.
No, it's the other way around. The cyanobacteria are there because of the anoxia. They don't cause the anoxia. The anoxia is caused by stagnating water, like I explained. And when that stagnating water builds up its ferrous phosphate, and that comes to the surface, And there's no nitrogen then, because the nitrogen was in the form of nitrate and that was breathed by the other bacteria. So you have a shift in the ratio of phosphate to nitrogen, I should say nitrogen to phosphate, which is normally 16:1, and in the Baltic it goes below 10, and can go even lower, much lower. And then you have excess phosphate. So when that water is illuminated by sunlight, then the standard algae grow, they take up all the nitrate, and then they stop the excess. And then they have a lot of phosphate left over, and also iron. And that's where the cyanobacteria come in and start growing. So they are an indication of anoxia at depth, and they don't cause it, because they float on the surface as scum, and they go out in the surface also when that water is lost. And as far as toxicity is concerned, I just know of stories where dogs went swimming, it came out of the water and licked their fur, and then they got sick or died, I don't know. But I mean, nothing kind of fantastic or sensational, right? It's just these individual assessments. And then people make a big fuss about it. I've swum in the Baltic in the middle of all these toxic algae. I mean, you don't go eating algae like that, right?
Are cyanobacteria in freshwater creating oxygen depletion?
No, they come in the summer after oxygen depletion has occurred, and then that oxygen depleted water comes to the surface. That's when you have the cyanobacteria. They're not causing it. The oxygen depletion is caused by normal algae that grow in the spring. When that nutrient-rich water enters the lakes, you have these big blooms and they sink. And in lakes, you have a zooplankton that can divide very rapidly, that have a parthenogenesis. They can do that very rapidly. The so-called cladocerans, Daphnia, that lot. So they can eat up all the algae in the water, but they don't like cyanobacteria. And that's again because cyanobacteria have this long tradition of not being eaten, which is why they're there. So that's that situation. And in the ocean, because the ocean doesn't have opportunistic conditions, they're favorable for opportunists. That's why the zooplankton is more closely geared to the phytoplankton. So you can have instances like with the spring bloom where diatoms grow in huge amounts, and they're not eaten because the zooplankton in the oceans have long life cycles. Many of them have take a year to grow from adult to adult, and some in the Southern Ocean 2 years. Then they're very small, they're as big as mosquitoes, the copepods. So they are incapable of reproducing rapidly. If something happens like a passing whale defecates and then that nutrients are taken up by phytoplankton, by diatoms, and they grow, those diatoms will not be eaten, not by standard zooplankton. But you have krill. Krill swims around. So in that sense, it's opportunistic because it has that size that it can swim large distances and go from patch to patch. So the zooplankton condition in the ocean is very different to the lakes, because in lakes you can have these zooplankton that opportunistically grow rapidly.
So one thing that I always hear, and maybe that's a misconception too, is that certain bacteria lead to decomposition of cyanobacteria or diatoms or other types of microalgae. So just to maybe summarize the former part, microalgae do not lead to oxygen depletion anywhere in the ocean. Oxygen depletion leads actually to growth of cyanobacteria, but microalgae does never cause it.
No, microalgae, when they sink out to the deep water, and that deep water is not being replenished, it's not being mixed, if it's stagnating. You see, there you can have these so-called anoxic zones. And the anoxia comes from stagnating water. And of course, if you have input of organic matter down there, which stays there and is broken down there, then you can build up these zones. But that again can be diminished by fish swarms that swim through it in the stagnating zones. And the fact that they are spreading, they're supposed to be spreading, these anoxic zones, there are several factors at play here. And one of them, of course, would be hydrography, that because the surface water is warming, so mixing is getting more difficult because of the stratification. That's one case. The other case, of course, as I've already mentioned, that these animals have been taken out. I mean, the fish have been taken out, and also the larger zooplankton like euphausids, krill type stuff. So that favors this accumulation of low oxygen water at the pycnocline. The pycnocline is density difference. You have a warm ocean on the top, and you have the rest of the ocean is cold. And where the two are separated, that region, because of the stratification, it doesn't mix that much. The less stratification you have, the more the mixing. If you have warm, light water floating on cold, dense water, then the transition is more difficult to break through than if the density differences were less. What a lot of people are not aware of or don't understand is that with the rise of the diatoms, these are the algae that have silica. They have a silica shell. And the silica shell is protection against grazing. And this was not believed for a long time. Because zooplankton, if you look at zooplankton feces, you always find these shells in them as well, right? But you don't find any pieces or remnants of the squishy, soft plankton because there's no shell left behind. So if they eat, let's say, 10 naked phytoplankton that don't have shells and one diatom, then that diatom shell will be there, but the other stuff not. So then people say, oh, they've been eating diatoms. So that's a misconception. But recently, very recently, just a couple of months ago, papers have come out now. This is a group in Denmark that's doing this work. They have been studying the zooplankton, these copepods, in great detail, and they found that they reject diatoms. And they reject them on the basis of shell thickness. They can guess that, right? I mean, in our case, if you are given vegetables that are soft, right? I mean, that are crunchy and soft. I mean, crunchy meaning chewy, no? Then you would eat that. But if you look at these grasses and things like bamboo and so on, they are glassy. I mean, there's not something you'd use your teeth on. And there's this saying, that you don't look a gift horse in the mouth because you don't want to see the teeth. Well, now this group in Copenhagen has shown that the copepods, if they're given diatoms, nothing else, their teeth wear down just like horse teeth. Same story. So they were the first people to actually look at the teeth of zooplankton, and they found, the ones that have been eating diatoms. See the ribs over there in the back, no, on your thing, right? Those ribs, I mean, those are like files, right? And the zooplankton also have teeth that are composed of silica, of the same stuff. So they rub down, right? So these diatoms then, because they're not favorite food of the copepods, they accumulate, they make the spring blooms. And since they're not eaten and they can't just stay there, I mean, there's no fortile, there's no advantage of not being eaten and staying there, right? They sink out. And they are the main transporters of carbon in the ocean for that reason. Right? So in the spring bloom, after the spring bloom, you have a massive fallout of carbon. And that is, I would say, about much more than 50% of the carbon input and sequestration and so on is due to these diatom blooms for that reason. I'm being conservative. It's more, right? Whereas the stuff that comes after the diatoms is the soft phytoplankton, because the diatoms also take up all the silica, dissolved silica in the water. When the diatom bloom is sunk out, then you have very little sediment sinking out after that. Although cells by nature are always denser than the water they displace. So basically everything in the ocean, all life in the ocean should be sinking, should sink out. But it doesn't, and we don't understand that.
In former episodes, we talked about Chaetosaurus being food for krill. So krill, do the teeth also wear down where they eat those diatoms, or are they built differently?
Good. You've been watching out. Fantastic. No, that is exactly the niche that krill is exploiting. That's why it's big size, because it can swim long distances. And the krill, they have their teeth in the gut. They have what is known as a gizzard. A gizzard is what the chicken also has. Birds have to take stones. They put stones into the gizzard. That's why they eat stones. And then the stones are doing the job. But in the case of krill, they have teeth in the gizzard. Internal teeth that look like the copepod teeth. That is the next step to study. I mean, the people in Copenhagen, I hope they start doing that. To what extent the teeth are renewed in the stomach, because they will also be ground down. Yeah, so the krill are doing that. They have evolved to feed on these diatoms that nobody else feeds on, because they can swim around and search for them, and then they can crush them in their gizzards. And the krill also have extremely powerful enzymes, proteases, as a matter of fact, enzymes that break down protein so rapidly that, I mean, they're amongst the fastest proteases on the planet. They used to be used for cleaning burn wounds in the past. So that was a krill fishery. It was catching the krill, and the proteins were extracted, and they were used to treat burn wounds. And so many cells are dead from the burning. The live cells below that, they then get infected by bacteria that grow on the dead cells and then go and attack the live cells. So you have to clean burn wounds, and they use this krill proteases for that.
And do you think there's a possibility that a type of zooplankton could evolve that could actually eat the excess cyanobacteria that we dislike in the ocean, and that would solve the problem of those types of blooms?
No, I don't know. There's no hope of doing that. I mean, if you could do that, you would do that in lakes, right? They would start eating the cyanobacteria in lakes, like the toxins. Microcystis has these toxins. They also have very potent toxins, amongst other things. Like they have saxitoxin. It's also been shown in cyanobacteria, like these deadly dinoflagellates. But that doesn't affect the copepods. It doesn't affect the daphnids either, because they don't have those kind of neurons affected by these kind of toxins. So this is a huge evolutionary game going on for ages, not this arms race. And I don't think we can get into that and change anything. No, we have to accept what's there. We can change the physical environment, but also a bit of the chemical environment. And we can change the crops that we would like to have, I mean, the animals that we would like to have by breeding and domestication. But I don't see any scope for creating zooplankton that would eat something which has not been eaten for millions of years.
So just to summarize, to fix the Baltic, we need to reduce fishing. That's one step. And we can't do much about the excess of phosphates and nitrates in the Baltic. And the sort of reputation of the Baltic is very bad. People always have seen or heard about these toxic algae blooms, and in the perception of people, it's like this is such a dirty part of the sea. Like people really have a negative impression of the Baltic Sea and would love to find some kind of regulations that would stop the toxicity. But
you know, not that I'm aware of mass toxic events in the Baltic. These are just species that we know are toxic, but when have there been animal deaths? I mean, there's seals also in the Baltic, and are there reports of seals being killed by toxic blooms?
No, I believe that this is the optics are toxic for people. They see an algae bloom and they believe it certainly must be toxic because of the microcystis in the freshwater that we are well aware of, that is creating ALS and Alzheimer's.
Yeah, and nodularia and so on, and these things. Yeah, you know, cyanobacteria, they can only develop dense blooms for this nitrogen fixation when the water is calm. But if it's perturbed, then not. And in the past, the Romans, they discovered that if you piped water to cities, the aqueducts, right, and then you had these pools, then these pools would have got this cyanobacteria on the top. So what did they do? They invented fountains. That's the reason why there are fountains in the drinking water. And we like the fountains because the fountains, they churn the water, so cyanobacteria can't grow. So the word for fountain in German is Brunnen, right?
Yeah.
And the other word for Brunnen is a hole in the ground, right? They both called Brunnen.
Yeah.
And it's very positive. Brunnen are very positive, right? Fountains. And wells, no? And in Germany have the same word. That's because in both the cases, the Brunnen, the holes in the ground are in the dark, there's no cyanobacteria, and there's also, so they were safe water. The Romans knew this. That's why they built these fountains. And in Northern Europe, they didn't have that. And that's when people died from drinking water. And that's when the first pogroms against the Jewish fellow citizens came up, because they were blamed for this. So the first pogrom started somewhere in 10th or 11th century in France, due to this poisoning of cows and livestock and so on. And what people don't realize is that there were no toxins. I mean, even if anybody wanted to do that, what could they have used? I'm pretty sure that it was cyanobacteria that led to this. And
Microcystis or?
Yeah, I mean, there are various other cyanobacteria genera, very common ones, that don't always produce the toxin. I haven't been following the literature, whether it's been discovered now, why and what. No? And this is also the reason why beer was so popular, because beer was safe. This is interesting. I can tell you even more about it, because beer is made from barley, not from wheat. I mean, okay, there are places in Bavaria where they make it from wheat, but here in the rest of the world, it's barley. But why barley? Because barley contains polyphenols that wheat and the other rye and so on, roggen and so on, don't contain. So barley straw is used today in Australia in the drinking water reservoirs to keep the cyanobacteria down. So this clean water idea came from the barley, because that would break down the toxins and would also prevent the cyanobacteria from growing. And in the past, in the fortresses and so on, where they had rainwater, and also in these kind of stinking pools, they would then drink beer. So the payment of soldiers in the past, 500 years ago, was beer. And that beer didn't make them drunk. It was just clean water.
If we switch the geography back to the Gulf of Mexico, I mean, the Gulf of Mexico, you mentioned that the source of macronutrients is the fertilizer from agricultural production. I think something like 40% of the wastewater in the US ends up in the Mississippi, and then you have all these large farming areas. So what happens in the Gulf of Mexico? So we humans are the source of macronutrients, and that leads to an excess of cyanobacteria. But the low oxygen and basically the overfishing in the Gulf of Mexico is one cause of the fish death in the Gulf of Mexico. But the oxygen depletion is not a cause of the excess macronutrients that end up through the river, to the Mississippi River in the Gulf of Mexico.
You know, the anoxia maintains the phosphate. If you didn't have anoxia, then the nutrients entering, they would be sinking out with it, because the water from the rivers doesn't have much silicate because of the agricultural runoff. So it's a lot of phosphate and nitrate. If it was diatoms, they would sink to the bottom, and then you would have the anoxia on the bottom. Here, a lot of that phytoplankton stays in the upper few hundred meters and is broken down slowly. I mean, it's diffuser. And then, as I had mentioned, you have this layer of low salinity water where the Mississippi enters. So you then have stagnation. And that's where you have these clouds of anoxic water. But I'm not aware of big cyanobacterial blooms in the Gulf of Mexico. Is that true? Has it been shown?
I just know that it has like this reputation of like harmful algae created through humans, created through excess fertilizer, and then being harmful for the fish.
There's a species of dinoflagellate on the Gulf side of Florida.
Yeah, that's also a wastewater problem in Florida, because they don't treat the wastewater before it enters.
Yeah, but I don't think this Carenia is the one that it's one of the worst toxic algae you can imagine, because it also gives off volatile gases that enter the atmosphere and lead to people having breathing problems, coughing and allergies and so on, right? So that is a really bad alga. Luckily, it only occurs there. It hasn't moved out. If it were to go to other tropical areas, that would be hell.
So it only exists in this place, only in Florida?
Yeah. Only on the west coast of Florida, yeah. It's deadly on fish, because if there's a bloom of this, I mean, it's not a dense bloom, it's just, where they're growing. If a fish swarm swims into this water, they just die. I mean, I've seen reports of this, credible reports, that the fish die kind of instantaneously almost. I don't know exactly how this works and what the algae get out of it. So this whole toxic algal story is kind of subsided now. There was a time when it was called hysteria, in the Potomac River in Washington. They also had fish deaths where fish would swim in and then die very soon. And this is also dinoflagellate, but it hasn't occurred for a long time now. This happened kind of end of the 80s, early 90s, and since then it's kind of all died down, more or less.
I think in Florida it still happened
it happened
years back.
This summer. But that's not a nutrient problem. It's just this alga doing its thing.
And those, from what I understood, in Florida at least, there was a problem with the wastewater of residents that basically pumped it directly into a river and a lake that then got into the ocean, and then the algae blooms happened. And if they had regulated the wastewater, human wastewater, it would have reduced the input.
It could be. You have to know the hydrography to be able to address that issue.
Interesting.